the last part of the notes for chapter 10 on gases, just some ideas, some things that can happen with gases. No more problems. I know you guys are like, ha, 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 don't give me any more formulas. Here's an example to show you what happens in a container with a gas. Because remember, these particles move independent of each other. And they're, moving around as fast as they possibly can. So it tells us what happens to gas laws in nature. Those are laws, okay? And each of the gas laws have discussed, what happens with the pressure, temperature, volume, etc. when you change certain conditions. So why, when you look at these walls, there's some other theories now. Now, when we did the gas laws, those are laws. Those are natural phenomena, okay? But there's also some theories about gases as well, okay? One of the things about gases is there's a large number of molecules, so they're going to be continuously in random motion. They have no set patterns, okay? They're just trying to get away and move around as fast as they can, okay? The combined volume of all the molecules in a gas is negligible. In other words, they're moving around so fast that it doesn't matter how many you throw in there. It really doesn't change anything. And then again, depending on the container they're in, if it's really small, that might be a problem. And again, we're going to talk about that. But when you talk about the actual molecules of gases, they are not attracted to each other. There's no attractive forces and there's no repulsive. There might be a little bit, but they're so small that they don't affect the motion of the gases. Okay. And again, this is a theory. Maybe later on they'll prove that maybe they are attracted to each other. Okay. And then the energy, when molecules run into each other and they have collisions, their average kinetic energy doesn't change. So they just bounce off each other and keep going. There's no energy transferred from one to the other. They just keep their own energy. It's like they ran into each other and I'm on my way out of here, okay? So because the average kinetic energy of the molecules doesn't change, it's not going to change the temperature, and those particles are going to still be in motion, okay? It's not like two solids running into each other. Eventually they're going to transfer energy and they're going to stop moving. It doesn't happen with the gas particles. Okay, so the average kinetic energy of the molecules is proportional to the, again, absolute temperature. That's Kelvin temperature, you guys. That's why you have to use Kelvin temperature when you do gases, because their kinetic energy is proportion to that absolute temperature. All right, so again, that's why we switch everything from from Celsius to Kelvin. When you do with solids and liquids, you don't have to do that. But gases you do, because that kinetic energy is proportional to it, okay? Why do they move so fast? Again, the higher the temperature, the faster they move, okay? Individual molecules actually can move at different speeds if they're a little heavier, a little lighter. But they show up here. There's three here, okay? The first one, and it's a little hard to read, is let's see, I'm trying to find, these are hard to read. This is the speed, okay? So this is the first one. This is the most probable thing. So as you increase the temperature, you increase the speed, okay? This is the average. These are the averages right here, okay? And then this is the root mean square speed. Not a big deal, you guys. It's their average kinetic energy, okay? But this is the most probable speed that they, as you increase the temperature, what happens? Their speed increases as you increase the temp. Okay. At any given temperature, the average kinetic energy, there's actually a formula for it. I've given you enough formulas, so I'm not going to expect you to know this one. We're not going to deal with this one. And again, molecular mass, the heavier it is, it's going to slow it down a little bit. Okay. Here's some of your gases. And you notice that the one that spreads out the most, but is the slowest, would be hydrogen, because hydrogen is the lightest. It only weighs 2 grams. Helium is 4, water's 18, 28, 32. So the heavier they are, they go fast, and it's a quick thing, and then they kind of mellow out. Whereas the smaller they are, it kind of takes them a while to get there, and they don't mellow out as fast. Okay. So these graphs is really based on their size. Okay. And again, we're not going to do this because I've already given you enough formulas. If I give you any more, there'll probably be a revolt, and I don't want you guys to revolt. So just wanted to show it to you. Okay, so if they have low mass, their speed is greater than the heavier one. Okay, all right. Some of the things to remember about gas particles is they like to escape. Okay, they like to move. They don't want to stay in it. So if you have a tiny hole in, and this is my volume, and see there's a little spot right here, a little hole, they will escape into that. Okay, that's called effusion. Okay, when they escape. There's also diffusion, which is the spread of one substance. When there's like with liquids, you know, if you have a higher concentration and a lower concentration, they want to equal each other out. They'll diffuse so that both pieces are the same or both parts are the same. Well, gases kind of want to do that too. They'll spread so one substance throughout a space is the same as a second substance. They don't like to have highly concentrated over here and low concentration over here. They'll mingle so they're both the same. That's diffusion. Okay, so effusion deals with gas particles escaping through a small hole, and diffusion is in a whole area where they're going to spread out and be even so that there isn't a high concentration in one spot and a low concentration in another. Okay, there are laws to describe it, and again, we're not going to worry about that. Okay, we've already done enough formulas, but they relate to their size and then how fast they'll diffuse. Excuse me. The lighter gases usually move at a faster rate because they're lighter, so it's easier for it to move. Okay, but again, I'm just showing these, giving you an idea, but we're not going to do any formulas with them. And then when we do all these gas laws, they're all for what they call ideal gases. Ideal gases are at high temperature, low pressure, and there's not a lot of volume. I mean, there's not a lot of mass to them. You know, their moles is slightly small. So there's ideal gas laws, and that's what we're dealing with. You can mess with those by changing things, having it at a low temperature, having it at a high pressure. So you can change the ideal gas laws and their relative behavior if you mess with the parameters. And again, real gases are high temperature, low pressure, and then the moles is low as well. There's not a lot of gas there. Okay, even if you just change the pressure, put them at high pressure, they start getting crazy because this is what they should be at ideal gas right here. And look what happens when you start messing with the pressure. They don't follow the rules. Okay, and again, we're dealing with ideal gases. We'll stick with ideal gases, but you can mess with their laws by changing some of the factors. Here's just showing you what happens when you change pressure. So this is where they should be, and this is what happens to them when you do that. Okay, and again, the deviations, the reason for that is because you're adding, you're changing the parameters. So if you have a higher pressure, what happens is you have more collisions. And when you have more collisions, they're not going to act like they normally would. So that's how you can deviate from the ideal behavior by when you increase the pressure. They don't have as much room to move around, so they're going to bang into each other, and then that's going to change things. The same if you have the lower temperature. If you have lower temperature, they're not going to move around as fast. They're not exerting the same pressure because, again, if you lower the temperature, they don't move around as fast. So you can mess with the ideal behavior by changing the temperature and changing the pressure. Okay, that's it. We are done with gases.